In the previous lab, the process of charging pieces of tape was examined, and students then determined the sign of their charges, their magnitude, and the ratio of charged to non-charged particles. This lab follows a similar setup, but is taken a step further in the magnitude of charge approximation by modeling the pieces of tape as a line of point charges with a uniformly distributed charge. The goals of this lab are similar to those of the previous lab, as they aim to allow students to examine how charges interact in a real-world setting, observe the ability of insulators to prevent flow of charge, gain an understanding of how charges interact with neutral matter, and improve their ability to calculate electric fields resulting from complex charges. This lab requires some knowledge of electric fields and the forces they can create. First off, it is known that opposite charges attract while like charges repel, the degree to which is determined by their distance and the magnitude of their charge. All charges create an electric field around them, wherein which a force could be generated by the presence of another charge. The electric field at a specific location can be determined by using this equation. And to determine the electric force, the charge at the observation location is simply multiplied with the electric field. It is also known that electric fields can be superimposed, so that to find the net electric field at an observation location, you can sum all the vectors of the individual electric fields acting at that location. The charged tape was created in the same method as used previously, with two pieces of tape being quickly pulled apart. Interactions were studied in the previous lab, and it was found that the upper tape would repel other upper tapes, while attracting bottom tapes as well as neutral matter. Once again, these same observations were observed. However, with more experience creating these tapes, the results were even more obvious. The interaction with neutral matter is a result of an induced dipole being created as explained in the previous video. This is caused by a nearby charged particle being in close proximity to neutral matter. The charged particles put a force on the positive and negative molecules in the neutral object, creating an induced dipole which can then interact with the source charge, creating an always attractive force. For this reason, the sign of the charge could only be determined by creating a repulsive force. This was ultimately done by bringing the charge near a positively charged pen, thus showing that the upper tape has a net positive charge. To determine the magnitude of the charge on the tape, two methods were used. The first was to create a single point charge estimation by making the assumptions that all the charge was located at the center of the tape, that both tapes had the same magnitude of charge, and that all forces acted at the center of the tape as well. This method then calculates the force of the tape to be its mass times gravity, and since the tape is levitating, there is no change in momentum, and the electric force can be assumed to be equal in magnitude. From these assumptions, a formula can be derived for the charge of the tape, and when the experimental values for the mass and distance of the separation were plugged in, a charge of 1.177 e to the negative 8 coulombs was found. This second lab asked to find the charge in another way. Using VPython, the system was modeled as a line charge in order to determine resulting forces and approximate the magnitude of the charge. This code works by first establishing constants to be used in calculations, such as the constant 1/4 pi e naught in gravity. Then the experimental observations are inputted, including the distance between the two pieces of tape, their length, and their mass. A function is then called which creates a line of point charges representing each piece of tape and gives it the assigned number of point charges, a uniformly distributed charge, a length, and a position. At this point, a total electric force variable is created and set to 0, which will be used to sum up all the electric forces acting on the top piece of tape. A for loop is then used to iteratively go through each point charge on top and calculate the E field from each point charge on the bottom. It accumulates all these E fields and forces, and when the final E field from the bottom charge is calculated, the for loop then calculates all the E fields for the next top charge, and so on and so forth. Along the way, the code creates arrows to represent the different electric forces, and by the end, it has a total electric force for the upper piece of tape, which is then displayed and compared with the force from gravity. The initial charge approximation can be adjusted until the two forces are equal to each other in magnitude. When this is done and the initial values for length, mass, and separation are inputted into the code, a charge of 2.577 e to the negative 8 coulombs was determined to be on the upper tapes. The difference between the two is 1.4 times 10 to the negative 8th coulombs. The more accurate of the two would be the line charge approximation. It still does rely on approximations, such as that both pieces of tape have the exact same charge, and also that the tape is simplified to point charges, just more point charges, and thus more interactions are being taken into account. For this reason, the more we break these pieces of tape into separate point charges, the more accurate the calculation becomes. So while this approximation is more accurate than the previous single point charge model, it is still not a perfect integral calculation. Ultimately, this model gave a much more accurate approximation of charge and allowed for the evaluation of the previous model. Ultimately, there was a 54.32% error between the approximation in Lab 1 and the approximation done in this lab.